Hello, everyone, and thanks for coming today to kind of like Modular Summit. And today I want to talk about a little bit of something that we've spent the past almost three-quarter of a year working on. But the story, as you'll see, is much longer than it currently seems like. So yeah, cool. All right, so quick introduction about myself. Before I started Argus, I was one of the co-creators of Dark Forest. Dark Forest, for those of you who might not have known, is the first fully on-chain game on Ethereum built using ZK snarks. That started with a simple question of like, what if we create a game where every single game action is an on-chain transaction? Back then in 2020, this was an absurd thesis. A lot of people was like wondering, like, why would you make a fully on-chain games? And how is this even possible with blockchain being as low as it is? But regardless, driven by our curiosity, driven our just like, our kind of the culture of just fucking around and finding out, we decided to build Dark Forest. And so this is like what Dark Forest looks like back in 2019, 2020. It's basically a space exploration game where thousands of players were fighting on chain to expand their empire. And within the first week of launch, we had more than 10,000 players or wallets and trillions of gas spent in the Ethereum testnets, attracting a large number of players. And eventually, we had to move on from testnets because other developers who want to test their applications were not able to. And eventually moved to a sidechain. And even in a sidechain that is supposed to be more scalable, it turns out that it is not as scalable as we think it is. We quickly filled up the entire block space, driving up gas costs and practically making sidechains unusable with only a single application. And so now begs the question, right? So with all of that limitations, why are people still so excited about on-chain games? Well, after Dark Forest, we've seen many people, investors, founders, builders, hackers alike, building on top of the legacy of Dark Forest with things like Lattice, building Mud, a library and framework to build on-chain games easier, and also content companies like Primordium building a fully on-chain games, and also things in other ecosystem beyond the EVM like Dojo on Starknet. The key thing here is that we realize that the limitations that we have with existing blockchain comes down to the fact that we are sharing a chain with everyone else. We are sharing this like very small room where there's not a lot of space with other applications that also want to use that. And so if you see on the chart there, you can quickly realize that if there's another game like Dark Forest living on that same chain, then there could not possibly, be a functioning chain. And so the question is like, what now, right? Do we just give up? Do we just like, kind of like just like throw away the concept of like on-chain games? And so we decided that no, we want to actually explore how we can build better on-chain games, and we want to make sure like that the game that we're going to build next is going to be scalable. And so we embark on a journey that starting with one big key realization, that we currently took blockchain architecture for granted. We have all these L1s and L2s, and yet they all look the same. They all will tell you very, very similar things. They'll tell you that our consensus is better. We have better trade-offs than the other blockchain. They'll tell you that their VM is faster. They'll tell you their VM is like parallelizable. Or they'll tell you that maybe if they're an L2, their fraud prover is better. Or how their other competitors, fraud prover doesn't exist, or like their other rollup is fake news. Some people will claim that their proving system is better. Like our ZK provers are faster, although we never see the benchmark. But all this war, to what end? To create yet another DEX that you can deploy on any other chain, like doesn't matter what VM it is, it all just looks the same. Or to mint yet another NFT that, again, you can deploy on any other chain. We decided to take a step back and think differently, think how we can actually see blockchain architecture from a different lens. We asked the question of like, what if we escape the classical blockchain architecture? Every blockchain that we've seen until now, it all looks similar to Bitcoin. all looks similar to Ethereum. It behaves the same way. You have the concept of gas, you have the concept of like transactions, like if people sign transactions, they submit it to the blockchain, and that causes a state transition. It all looks identical to each other. And another key thing that we realize is that other people and other blockchains, let it be L1 or L2, they're all trying to build a blockchain for everyone. And I'm not saying this from like a wholesome way. It's more of the fact that like they don't really take into consideration a specific kind of use case or a specific kind of user persona, and instead they just try to build something that everyone will just like assume is compatible with their product in mind. We took a different direction. We choose to build the best blockchain for a very, very specific user in mind, in our case being players and game developers. And so, again, we asked this question, and it comes down to really understanding how games are vastly different than your typical applications. So, for example, like an application that you might use a lot is things like social media, like Twitter, and the other kind of things would be games like Minecraft on the other hand. And so here we can see that with Twitter, Twitter acts in this very straightforward way where if you write a tweet and then you click a button, then you will have your tweet posted. One thing to note here is that every time you click a button, there is a user input event, and this is what triggers the state transition. This is what I typically like to refer to as an event-driven runtime. As you can see, this is very much similar to how your typical blockchain would look like. A user would want to trigger an event, and they would click, send a transaction, and that transaction would be inflicted. But if you see games on the other hand, games doesn't behave the same way as a web application. Even without user input, even if you're AFK, if you're just going away with your brother, state transition still happens. Fire will continue to cause damage, water will continue to flow, wheat will continue to grow, and day and nighttime will continue to move. And this is what we like to call the loop-driven runtime. Key thing here is that no user input is needed to cause a state transition. And so, drawing an example back, you will notice that the web app is, again, very similar to smart contracts. Let's say in Uniswap, a user wants to trade token A and token B. You would submit a transaction, and that trade is executed. Again, event-driven runtime. We realized very quickly this event-driven runtime nature of a classical blockchains are just not compatible to run a game state machine. And so we kind of explored deeper the loop-driven runtime that game has. And again, all game engine is specifically built to support this loop-driven runtime. The key thing with the loop-driven runtimes is game progressions and how times are organized within the games is referred to as a ticks or the atomic unit of time. Each game loop is going to be executed in a single tick, and the higher tick rate that a game has, the more the game feels more responsive. If you played a game like Counter-Strike or Valorant, you'll notice that these games have 20 tick rates or 60 tick rates for the modern game servers, while games that are more old, they'll typically have lower tick rates, and often you feel sluggish, doesn't feel responsive, right? In blockchain, you can treat these ticks to something that's analogous to a block. It's basically a single unit of time where state transition happens. If a tick or a block feels late, you visually and feel lag in the game. And if you've built games before, or even you've played game, you know how suck it feel when your game move lag and you die and you get killed, and they would rage on to the enemy or the game developers. It's not a pleasant experience. And so, at the end of the day, we believe that games are loop-driven in nature, and because a lot of game state transitions are not triggered by external input. For example, a gravity doesn't rely on the user pressing the W button to move forward. Gravity will continue to exist regardless of user input. There's also a case for deterministic transaction ordering. Let's say if you want to inflict a damage to your user. Should the game heal apply regeneration to the HP of the user first, or should it inflict damage first? With a traditional ordering of this random builders of the typical execution layer, let's say the EVM, you can't predict or you can't like deterministically control which state transitions are getting applied first, and as a result, you have this deterministic transaction ordering problem that causes reliability issue in the game loop itself. On top of that, you can also allow for more aggressive parallelization by using like data-oriented system design in these loop-driven runtimes. Last but not least is that while some people might thought about retrofitting event-driven runtimes like DVM into a loop-driven runtime, we've seen that this like leads to a lot of issues because of the nature of like how you do gas metering, like how do you do accounts, that is not as simple as just like calling a loop or calling like a single smart contract function again and again at every block. And so if you have a layer 2 rollup with a loop-driven blockchain for games, what unlocks do we get? The first thing is, of course, we want to maintain the composability. Making the blockchain from event-driven to loop-driven doesn't mean you have to sacrifice composability, and that's actually the reason why we want to use blockchain as a runtime for these games in the first place. On top of that, with a loop-driven game runtime, you can have real-time gameplay, where you can now start to blur the line between a blockchain and a traditional game server, and eliminating the concerns of building a game on top of these rollups. With a idiomatic runtime, like with the loop-driven runtime, you could also build more complex games than you can before in a blockchain. There is a reason why most quote-unquote games that you see on the blockchains are mostly just people minting NFTs, because that's really what the easiest you can do when you can only have event-driven runtimes. And last but not least, the more that you can emulate a traditional game engine runtime, the more that you can just treat the user experience much like playing another game. But with all those good things in mind, we still are missing one key ingredient to build a scalable game server blockchain. And the key thing there is the fact that we also need horizontal scalability. When you're playing a game, you are not only playing it on a single server. If you play MMOs, MMOs are comprised of many, many servers. If you're playing Counter-Strike, these Counter-Strike games are spread out across different sessions that is run across different computers. But if you realize, at the end of the day, a rollup runs on a computer. And so they are bound to the physical limitation of computation itself. And so games and most large-scale applications scales using multiple computers. But if that is the case, then why don't we just spin another rollup then? If we do the naive approach of just spinning up another rollup, we can lead to composability fragmentation. Smart contracts would stop talking to each other. And while there are kind of different construction of shared sequencers, a lot of these constructions are less than ideal for gaming use cases. For instance, you might have to depend on cryptographic security to prevent things like locks, DOS vector. And doing atomic shared sequencer construction can also lead to constraints on execution layer. As a result, we need a new strategy to sequence rollup transaction. And to search for that, we had a gift from the past. Again, we'll look into how traditional game servers, especially those with intensive performance expectation, like massively multiplayer online game like World of Warcraft, RuneScape, Ultima Online, and whatsoever, through the concept of sharding. With sharding, some of you might have known this concept from databases like MongoDB, but the reality here is there's this conspiracy theory that the concept of sharding itself comes from game servers first instead of the database first. And so how does sharding work in game? The key thing here is that there's no one-size-fits-all problem. Again, at the end of the day, shards are just tool in a toolbox, not a prescription of how you should build your game. So for example, in the first sharding construction, you can use location-based sharding where you can split, let's say, a Cartesian coordinate into 4 diagrams. And when a player wants to cross from one shard to another, you simply send a message to other shard, and then the player would be teleported to the other shard. The second construction is by using something that we call multiplayer sharding. If you've played MMO games before, you might have seen that when you log in, you have multiple servers that you can choose. This is the same construction that you can do, where you can have distinct states or distinct game worlds that the players can decide to join. So now we have all the ingredients here, right? We have the loop-driven runtime, we have the horizontal scalability, and we also want awesome composability. All of this sounds great, but how do we achieve this in a rollup, right? This looks like things that on the surface seemingly looks like beyond the reality of we can get from a blockchain. But this is why we created Roll Engine. We realized that we can't just use a normal rollup and expect that it will run the way that we want it. We took it to our own hands to actually build the solution that we need. The same way that back in the 1990s, when you want to build a 3D game, there's no 3D game engines available out there. You have to build them by yourselves. And so the World Engine is, again, divided into two key parts. The first one being the core, which is comprised of two key elements, which is the EVM base shard, which is a hybrid execution layer and sequencer with sharding support. And the second part is a game shard, which is a high-performance game engine plus execution layer. And on top of that, you have peripheral components like the transaction relay and netcode to do the client-server communication, and also things like ZK Cloud Prover for you to have ZK games like Dark Forest. And so the World Engine core really comes down to our very specific design of our sequencer. While other shared sequencer construction would optimize for having atomic composability, we decided that atomic composability are extremely overrated, especially when you're operating on the context of games. And that's why we went full asynchronous, and so we don't have to put locks on the runtime. On an EVM-based shard, we have a global EVM chain where players can deploy smart contracts to compose with games, create marketplaces, dexes. We built this on top of Polaris, which is a Cosmos SDK compatible EVM module that allows us to customize the EVM to a much greater extent than what we could by, let's say, just naively forking it. On top of that, we have the game shard, which is running on top of the EVM-based shard sequencers, which is a high-tick rate mini blockchain designed to serve as a high-performance game server. The game shard is also designed to be state machine and VM agnostic. We built an abstraction layer much similar to Cosmos SDK EBCI so that you can customize the shard to your liking or build your own by implementing a standard set of interface. We have also built the first game shard implementation to provide an example. And we use an entity component system that is commonly used by game engines, and with construction that prioritize entity component system as a first-class citizen. So every single object or every single primitive on the state machine itself is treated like an entity. So things like accounts are a part of the ECS. Transaction is a part of the ECS system. It also has configurable tick rate, so you can customize your game to be as fast ticking as possible, or you want to slow it down to prioritize more number of entities. And the best part of this is that you don't need to rely on indexers. You can have fast reads on a blockchain without having to have this lack of eventual consistency indexers like what we currently have with Mud, Dojo, and whatsoever. And my favorite part of all is that you can write your code in Go, so you don't have to wrestle with smart contract languages that can be very limiting sometimes. And so the key thing, again, as I mentioned, shards are agnostic in nature to our abstraction layer. So you can build other shards construction, like a Solidity game shard, to complement your Cardinal game shard. You can also build NFT minting shard that have custom rules by let's say custom mempool and ordering construction to solve the basic minting noisy neighbor problem. You can also create a game identity shard to use NFT to present your game identity and allow you to trade your game identity as well. And again, we don't use locks, and as a result, we don't have to deblock the main thread, and making the game shard runtime as reliable as possible and not causing any lags, and we don't have to rely on crypto economics construction anymore. On top of that, we also have many interesting shard properties, like how each shard can have different batching compression strategy, and you can also geolocalize shards to reduce gameplay latency. And last but not least, you can also run game shards as an independent game server onto its own, so you don't have to worry about roll-up deployments on day 0. And so we've built many various games on top of the game shards. We've built a fully on-chain Agar.io, which have traditionally not been possible using our full World Engine sequencer stack, game shard, Nakama, and so on and so forth. We've also worked with a hybrid model where you would use existing game engine frameworks on Solidity and combining that with a World Engine. And the future is for you to decide. You can use our Cardinal stack, you can do hybrid, you can build your own game shard. It's basically Kubernetes for on-chain games. It's mix and match Lego for your games. And so now you're able to try out the World Engine. It's now open source on our GitHub. We are welcoming new contributors. For people who are interested, feel free to reach out afterwards. And if you're interested in building your first World Engine game, we are having a workshop later today at 11:30 a.m. at the Kaji stage. And then tomorrow, we're also going to be hosting the gaming track. We have a panel, and we also have a talk about on-chain games at the Fourier stage. And again, last but not least, the key takeaway from my talk would be that let's build cooler rollups. We're right now at the rollup renaissance, and what we already know is that, of course, rollups allow you to scale a blockchain. Of course, rollups will allow you to tap into the security of the underlying L1. But right now, we're still living this on this very EVM-centric conception of rollup architecture. This is the starting line and not the end. What we want to go towards is a user and application-centric rollup construction where people can build cool shit. And yeah, that wraps my talk, and thank you for listening.